Hello, welcome to another problem session. Um, we have a problem today in energy. So this is from the energy chapter. It's about conservation of energy, applying it to a universal gravitational force situation. So this situation is that this is Earth, and here is a equator, and there's a satellite sitting there, and then somehow it's shot, and then satellite ends up over here. Let's over here, and it's going in a circle, the larger circle. And then the rest of the machinery, like rocket, has to supply, rocket fuel is used to supply that. So just overall it's called rocket is supplying their energy. So we have a situation, say initial here and situation final here. The difference in energy is what the rocket supplies. So EF minus EI is this is what the rocket supply. Okay. Now the formula for these we need to figure out. That's what it looks like, right? So at this time, when you are looking at the rocket, it will appear the rocket is at rest, right? So it will appear the kinetic energy is 0. So if you just look at this will be equal to kinetic energy plus potential energy. We'll come to potential energy next, okay? But let's look at the kinetic energy. It will appear it at rest. So you think kinetic energy is 0. Kinetic energy I is 0. But this whole law, the way we've derived it, is in a inertial frame. This is 0 with respect to rotating Earth frame. And because a rotating object is always accelerating, that means this frame is accelerating, and so this frame is not inertial frame. So this is not inertial frame, not an inertial frame. So I can't use this, okay? So this is kinetic is not 0. So we need to figure out what's the kinetic energy will be. So mass of the satellite and its energy, its speed this time is squared. So what's this speed? That's the one we need to figure out. We are trying to figure out per kilogram. So we can either set this equal to 1 or just later on just divide by ms, okay? But this is what we need to figure out. So how do I get VI? Well, if you look at inertial frame, which is fixed to the center, in that frame, let's say this is the x-axis and this is the z-axis, and this is the maybe call it X, and this is Y. Z-axis that way. And this is not rotating, always in that direction, and always in that direction. So in that way, what you see is this guy's your satellite is going in a circle with Earth, just like surface of the Earth. At the surface of the Earth is going to go. So this should be VI should be 2 pi radius of the Earth. Just one circumference it went, and it went in 1 day. T equals to 1 day. So that's much time, 1 day, and radius of the Earth is this much. So which means we figured that out. So we figured that out. I'm not going to complete the calculation yet, and then we need to look at this. Now, person will say mgh means how much height of the Earth, but that's actually only applies near the surface of the Earth, and you'll find out that actually this F is about 6 to 6.5, about 6.5 times the radius of the Earth. So it's pretty far away. So I won't be able to use mgh. So mgh h equal to 0 will mean 0. We can't use this, okay? So we have to use the full G Newton and mass of the Earth, m of the satellite, over the distance which is radius of the Earth from the center. So it will be, the distance is this, and this minus is important because at infinity, if you have a satellite infinitely far away, is the 0 of this potential energy formula. So this minus is important. So let's see what we have. We do have RE done, MS will set to 1, and mass this. So this is also known. This also known. So this whole thing is known by this calculation. So what's going on over here? So that's the one we need to figure out. And so at this point, it's some distance r. The radius of this is r. This radius is r from the center, and it's going with some speed v. Or one's call it v final if you like. Well, so EF will be half mass and VF square, so that's kinetic energy, plus potential energy. You'll have a formula like this, but it's going to be minus G m Earth, m of the satellite, over this distance r. But we don't know r or we don't know VF. So where do we get these? So it turns out like we need to figure these guys out. Okay. There is a because it's going a circular motion, and the force is force of gravitation of the Earth, then we can apply the uniform circular motion. So this is one formula, and second formula would be uniform circular motion on satellite. When you apply that, hopefully we'll get all of that. So let's see. You have force of gravity is will be G. This time is positive. This side, this positive direction. M Earth, m satellite over r squares. So that's the force, and that's going to be ms v vf square over r. So this is another expression which is it has two unknowns here. So that's not enough information. This is one. Then the third thing we can notice is actually VF and R are not independent, because I go 2 pi in this 2 pi R on this arc, and because this is geosynchronous, very important, this is geosynchronous. Geosynchronous means it's moving with the earth, so it goes around in one day. So it kind of always facing the same place. So if it's on this side, it's facing this side of the earth when the earth has rotated that much. So this is 24-hour. So I will say V final should also be equal to 2 pi R over 1 day. T is 1 day. This T is 1 day. So now these two are certainly two equations and two unknowns. Unknowns are VF and R. So we should be able to solve for both of them. Let's carry out the algebra, and you can say I substitute over here, and then simplify, and that will give us R is equal to this formula where we know all the R, and plug into here. I'm gonna get VF equals to 2 pi R over T. Okay, so going back, tracing back, we figured out R because everything here is known, and we have figured EF. So EF got figured out, and now we have both of these, both EF and EI figured out, and then we should be able to get the answer, right? So putting it all together, we get, let's summarize the formula so we can plug in numbers at the end. Okay, so delta E should be equal to kinetic energy final, which is a half. I'm going to also divide by ms everywhere, so that's the thing we want to find, right? So I'll be half V final square, and I'm going to put together this potential energy with this other potential energy. I'm going to put in one place, half VI square. So this is change kinetic energy per unit mass, and then I have this guy is minus, but then this guy becomes plus. So we can GME and GME, let's see, GME common, so 1 over RE minus 1 over R. Okay, now having obtained this independently everywhere, we can plug in the number and get the answer. So this answer will be, work out the numerical value, and I'll be back. So to do this calculation, probably it's a good idea to just pull RE out, and so you can just get a simple ratio here. And then I went ahead and got VI calculated, and then I calculated R, and then got the ratio. So I'm anticipating that the case, and then from there I get the VF, and then for this factor I just calculate separately. Now I can put all the numbers into this formula, and it gives me 57.68 megajoules per kilogram. Okay, so just to recap, what we have done here is in calculating this, first thing we really needed to know that what this means. What this means actually went into figuring out a speed with which this thing will go. All right, so that was the definition I needed to know. And then I started out by energy consideration, and then work part by part. What do I need? And this was important here, that this formula is, I need to look from a inertial perspective, inertial frame. It's very important to know when your formulas apply. Whenever you're using Newton's law in F equals ma form, for instance, or a conservative energy formula form, you always are referring to a frame in which a frame itself is not accelerating. Okay, so I need to figure out a fixed frame, not a frame which is rotating. And in that frame, I can't say the kinetic energy is zero. Of course, in a rotating frame, it looks like it's zero. All right. And if you look at the what has this kinetic energy, then comes in here and subtracts. If you look at here in the final answer, it's over here. And the way it turns out in our formulas here, that this is actually very small compared to this. And it doesn't make a very big difference in this particular problem. But if I wasn't working with the geosynchronous orbit, where this thing is very far away, okay, it was going in a more closer orbit, where this thing, where the orbit was close by, it may have made a difference. Okay, so you have to know at what speed it will make a difference. But a priori I can't tell, so I really have to include that here, And sometimes people don't include it and they get a number very close to this and they think, oh, you don't have to include it. But in principle, you have to include it. Okay, so that actually, so I need to do, this initial was very easy, final was then turned out to be a whole bunch of unknowns in the final. And I needed to work out final by being not only applying the uniform circular motion, but also that it's going in a circle, and so there has to be a relationship in the speed and the radius of the circle. Okay, and this is where the geosynchronity played a big role, because I need to relate them. I needed to know if the period, what the period was, and period was 1 day. It actually didn't say period was 1 day. It said the same information in another word, geosynchronous. And sometimes people say, okay, what does this mean? And I'm not giving them enough information, but actually that's what the information was hiding. The last point I will make is whenever you're doing a very complicated formula like that, and you have to put numbers, it's always a good idea to work out the numbers part ways, each independently, and then you can put it in here. Okay, so I'm going to stop here. I hope you got a bit from this video. We'll talk to you later in another video. Bye.